Last time, we were looking at elementary objects, or seemingly elementary ones, water, springs. Even those can demonstrate really paradoxical behavior. Now we're going to move away from everyday experience to the extremes, very small, very fast, very light. And when we do that, the paradoxes just proliferate. We're going to talk about a few of the many paradoxes of modern physics. Two really big topics here, relativity and quantum mechanics. Paradoxes of these two could be almost an entire course. We're going to concentrate on a few really important and highly mathematical puzzles. Einstein supposedly said, "Common sense is that layer of prejudices laid down in the mind prior to the age of 18. These paradoxes, and modern physics in general, they really challenge our common sense, as he described it. All of our life experiences are on the scale of the human body. We're used to speeds up to, maybe in a plane, 500 miles an hour. Sound travels faster than that, about 770 miles an hour. Light? If you fly for an hour at the speed of a plane, 500 miles an hour, light takes 0.0027 seconds to go just as far. 0.0027 seconds. My watch would still read 00. You wouldn't even register. Our common sense breaks down at these high speeds and with really small or really large objects. These paradoxes, they really just show how different the world is at very high speeds and small scales. If we were small and light like electrons, these wouldn't be paradoxes. This would just be our everyday existence. In the late 1800s, physicists figured out that light doesn't travel like objects do at our scale. There's a ball thrown at you at 100 miles an hour. If you move away at 20 miles an hour, it appears to be going just 80 miles an hour relative to you. The Michelson-Morley experiment, that showed that light moves the same speed independent of the motion of the observer. There were other experiments that showed that fast particles don't behave like Newton's laws would suggest. Einstein's basic idea was that light will always be observed at the speed of light, a constant, 186,000 miles per second, roughly, 3 times 10 to the 8th meters per second. If you're moving away from the light source, the light doesn't appear to be going slower. It's still that same speed. If you're moving toward the light source, it doesn't speed up. Still that same speed, c. The second big rule of Einstein's when talking about modern physics was that the rules of physics are the same at any constant speed. If you're traveling in a smooth train at a constant speed, if there are no windows, there's no way to tell that you're actually moving. These simple ideas have some really surprising implications, paradoxical, or at least incredibly counterintuitive because of our common sense. Amazingly, there's very little mathematics needed to jump in and see some of these things. We really need that distance is equal to rate times time, and we need to know the Pythagorean theorem, that in a right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. So, imagine our producer, Eric, who's standing on a train platform, watching Sam go by on a train at some speed. We'll call it v, meters per second. Now, Sam has a light on the train floor, and it's pointed straight up to a sensor at the ceiling that's h meters above. Sam's perspective on the moving train is that light goes straight up. But Eric's perspective on the platform is that light starts out and moves diagonally because the whole thing is moving. And when it hits the ceiling, the train has moved. How long does it take for the light to hit the ceiling? It's a trickier question than it sounds. Let's first look at Sam's perspective on the train. If we're on the train, light travels h meters and has speed c. The distance is the rate times time, and so time is distance over rate. It's h over c. So Sam sees all of this happen at h over c seconds. The light starts at the bottom, hits the sensor at the top. And now we can check our work. Mathematicians and math teachers love to find another way to solve a problem so you can check your work. So let's switch to Eric's perspective on the platform. The amount of time needed from Eric's perspective, well, let's call it delta t. And let's see if we can check the delta t is actually equal to h over c. You see, Eric sees this light move diagonally, so we can draw a triangle. The height is still h meters, and we need to know the horizontal leg of this triangle. That's how far the train moved in delta t seconds. Rate times time is that distance, and so you get the velocity of the train, v, times delta t. The hypotenuse, that's how far the light went, according to Eric. Let's call that z. The Pythagorean theorem says that the sum of the squares of the legs, that's v times delta t squared plus h squared, is equal to the hypotenuse squared, z squared. We can solve this for z, and we get that z is the square root of v delta t quantity squared plus h squared. That's the distance the light travels in delta t seconds. Again, the distance is rate times time, where z equals c times delta t. We plug in what we figured out for z, the distance, and we get that z, which is the square root of v delta t squared plus h squared, is equal to c times delta t squared. We can solve for delta t. We can first square both sides and then add v delta t squared to both sides. We solve for delta t and we simplify a little bit by factoring out a c, and we get that delta t is equal to h over c times 1 over the square root of 1 minus v over c squared. And our work doesn't check out. You see, on the train, Sam saw the light travel and takes h over c seconds. From the platform, Eric saw the light travel in a slightly different way because it was diagonal, and because of that, the time it took was h over c times 1 over the square root of 1 minus v squared over c squared. We're off by this factor. Notice that inside the square root, it's -1. It's less than 1, rather. So the square root is less than 1, and so the fraction here is bigger than 1. If v is a normal speed, say even 500 miles an hour, this factor is very near 1. So 1.000003. You need 12 zeros in there. The train and the platform time are really essentially the same. But if v happened to be near the speed of light, let's say v was 75% of the speed of light, then this factor, which we usually call gamma, the Lorentz dilation, is about 1.5. That's saying that time goes about 50% slower on the train compared with on the platform. If you move up to a v being 98% of the speed of light, the dilation is more like 5. 5 times. Amazing. Simple assumptions that light is the same speed for everyone tell you that time is different for people traveling in different speeds. Now, before we see some of the paradoxes related to this Lorentz dilation, let's look a little bit more closely at this formula. Notice what happens if v equals c. If v is c, v over c is 1, and 1 minus 1 is 0, and we have a square root of 0 in the denominator. That's telling you that as v approaches c, as we get closer to the speed of light, the dilation factor goes to infinity. Now, that can't happen. Nothing except light and other electromagnetic waves can go the speed of light, but if you did, this is saying that time would stop relative to other people's sense of time. Your common sense says, no way. Your common sense, which deals with slow, heavy objects, not super fast, super light ones. In this sense, it's just wrong for these small, fast things. So why is it that they thought this might be right at all? There were a host of experiments that showed that Newtonian physics wasn't right for small, fast things and for light. Before Einstein, physicists knew that Lorentz contraction worked, that it predicted the outcomes of the experiments. What Einstein provided was the reasoning. All these other theories they had, they failed to predict one or more of the outcomes from these experiments. It was Einstein's relativity that predicted each one exactly correctly. So let's turn to some of the paradoxical results of this. The first one I want to talk about is the twin paradox. Imagine that two twins, we'll call them Julius and Vincent, were born on Earth, and Vincent quickly hopped on a spaceship and went away at 98% of the speed of light. Vincent comes back around and returns home when he's 10 years old. How old is Julius? Let's do the math. Julius, the one who's on the platform, and Vincent here is on the train that goes away. For Julius, how much time did Vincent's trip take? See, at 98% of the speed of light, the Lorentz factor is About 5. In Julius's time, Vincent's trip took 10 years times 5, times this factor, about 50 years. They were born as twins, and now Julius is 40 years older. Relativity and this time dilation, it implies that people don't have to age at the same rate. The Fountain of Youth, it's not in Florida where Ponce de Leon was looking for it. It's in near light speed travel. Now, technically, we should be using Einstein's 1917 general relativity, not his 1905 special relativity equations. See, special relativity assumes a constant velocity like the train. In general relativity, the mathematics is significantly more complicated, but it solves problems for accelerating and for turning. That's what would need to be done if somebody went away from the Earth and then came around. They would have to turn around at some point. So the twin paradox, is it real? Not only is it real, but it's incredibly important. You might use it every day. You see, GPS, global positioning systems, they use satellites to pinpoint the location to within just a few meters. And they rely on incredibly precise timing. If they're off by a few microseconds, millionths of a second, the GPS readings you get will be off by about a kilometer. If you don't take special relativity into account, the satellite clocks will be off by about 7 microseconds per day. That would give you GPS drift by about 2 kilometers every day. If you don't take general relativity, the more complicated theory, the one that includes gravity, GPS drift would be about 11 kilometers per day. Imagine turn-by-turn directions using satellite navigation. If they were off by 11 kilometers more every day, it'd be impossible. All of these things wouldn't work without understanding relativity. Once you understand relativity, you do have to agree that twins might not age at the same rate. The twin paradox, as yet, no one has figured out a way to do it. We can't travel that fast. But in theory, it's exactly correct. All right. We know that time is strange now, but it turns out that lengths are also very weird. So let's revisit Eric and Sam, Eric on the platform and Sam on the train. They agree on velocity. You see, Eric sees the train moving left to right at velocity v. Sam sees the platform and Eric moving right to left at velocity v. So, how long is the platform? Now, Eric, who's standing on the platform, might measure it and get like L meters. Now, you could watch, you could figure out how long does it take for Sam to go from one end of the platform to the other. Delta t seconds, we'll call it delta t seconds, and then you can check that the length should be v times delta t. But Sam can measure it in a different way, with a stopwatch. Time at one end of the platform to the other. Let's call it delta t prime. We'll use primes for Sam's measurements. We can calculate that the rate times time should be v, which they agree on, times delta t prime, which they might not. In fact, we know that they don't agree on the times. The times are different. The time is longer for Sam by a factor of exactly this Lorentz factor, gamma. So we put these equations together, and Sam measures the length of the platform like this. L prime, what he thinks of as the length, is v times delta t prime. Delta t prime is delta t over gamma, and so we have v times delta t over gamma. V times delta t is exactly the length as measured on the platform, and so we really have L over gamma. Just like time was shortened, lengths are shortened as well. Let's be really clear about this. Inside Sam's train, everything looks normal-sized. Things outside, which are traveling at v meters per second, they're shortened by a Lorentz factor, which is always bigger than 1. If Sam goes by at 98% of the speed of light, he sees the platform as 1/5 as long as Eric sees it. Just like time was shortened, lengths are shortened as well. And here's the weirdest part. Sam sees something that's flying by his window, like the platform. He sees it as shortened relative to how long it would appear if it moved with him. But remember the second part of Einstein's theory, that physics rules work the same in any constant velocity frame? For Sam, the platform is whizzing by at v meters per second. For Eric, the train is whizzing by at v meters per second. If Sam sees the platform is shorter than Eric thinks, then Eric must see the train as shorter than Sam thinks. Length contractions must work in both directions. If something is moving relative to you, you see it as shorter than it would be if it were at rest relative to you. This is kind of mind-bending. If Sam and Eric both hold meter sticks parallel to the train, Sam sees Eric's meter stick as too short, and Eric sees Sam's as too short. Now, of course, at normal speeds, even things like 500 miles per hour, the effect of this is incredibly small. But this length contraction, it leads to the following very strange paradox. Suppose you have a train, 1 mile long, traveling at 98% the speed of light. So the Lorentz factor now is about 5. And this train goes through a tunnel that's 1/3 of a mile long, through a mountain. Now the mountain is at rest, so from its perspective, the train is length contracted by a factor of 5. So instead of 1 mile long, it appears 1/5 of a mile long. The entire train, which was 1 mile if it were at rest, now fits into the tunnel, which is only 1/3 of a mile long. That's strange. In fact, if there were emergency doors on both ends of the tunnel, you could close both of those doors for an instant, and the train is trapped in the tunnel for that one moment. The 1 mile train inside of the 1/3 of a mile tunnel. Okay, that's weird, but it gets weirder. Hop on the train? What's the tunnel look like from the train? See, the train appears normal length, 1 mile long. The tunnel is moving backward at 98% of the speed of light. Gamma equals about 5. Since it's moving, you see it as length contracted. It's not 1/3 of a mile long. You see it as 1/3 divided by 5, 1/15 of a mile long. That's just about 100 meters long. That's it. Wait, so if the train is longer than the tunnel, in fact 15 times longer, how could it possibly close the 2 doors at the same time and trap the train inside? That's the paradox. From the outside, it looks like the train fits inside the tunnel. From inside the train, it's not even close. The train appears 15 times longer than the tunnel. Whew. How could both of those be true? That's a real mind bender. Let's see if we can resolve this paradox. There are 2 claims here about the order of events. One event is the front of the train leaving the tunnel, and the other is the back of the train entering the tunnel. And the paradox really comes down to this. A stationary viewer sees the second, B, the back of the train entering the tunnel, as happening, and then A, the front of the train leaving the tunnel. The viewer on the train sees A happen first, and then B. They see the front of the train leaving the tunnel, and then B, the back of the train entering the tunnel. The resolution? They're both correct. You see, if 2 events happen in the same place, everybody agrees on their order. But if 2 events happen in different places, opinions can actually differ on which came first. Not only are time and length relative, so is simultaneity. Imagine you see a flash of light in the middle of a train. On the train, the light hits the left and the right walls simultaneously. See, light travels the same speed in both directions. And note the ends of the train don't move relative to someone on the train. Light moves through time. It's the same speed in both directions, the same angle, the same distance in a given time. If you're on the ground, now you see the ends of the train cars are moving, and they're moving to the right. The flash happens right in the middle of the train, and then let's look what happens. In fact, let's go back to Newtonian thinking, pre-relativity, and see what that would say. If Newtonian mechanics were correct, and keep in mind it's not, but if it were, the light in front would travel faster than c. It would travel at c plus v, whatever the velocity of the train is. And that contradicts Einstein. But the light in the back would travel slower, c minus v. It travels a shorter distance horizontally in a given time. So exactly correct that the light hits both ends at exactly the same time. Newtonian mechanics predicts that simultaneity is preserved, that 2 events happen at exactly the same time for everybody, not just for one person. If two things happen at the same time for you, they happen at the same time for everybody. Einstein's relativity says that that doesn't happen because light never moves faster than c. It's the same velocity for all observers. See, Einstein says the person on the ground sees light move at the same speed, at c. So let's ignore the train for a second. The light flashes at some point in space, ignoring the train, and it moves in both directions at the same speed. And now when we put back in the ends of the train, light is heading toward the back end of the train, and that hits there first. And then light hits the front end of the train, not at the same time. What was simultaneous on the train is not simultaneous to other observers. And the train tunnel doors problem is a similar thing. On the ground, the tunnel doors are closed at the same time. On the train, the front one opens before the back one closes. So, what's really going on in this train in the tunnel? We want to pay close attention to 4 events. I'll label them A through D. A is the front of the train enters the tunnel. B is the front of the train leaves the tunnel. C is the end of the train enters the tunnel. And then D is the end of the train leaves the tunnel. In what order do these things take place for each of these observers? Let's start on the train, which is 1 mile long, going through the tunnel, which appears 1/5 of what it is at rest. It appears 1/15th mile long. Now, on the train appears at rest, and the tunnel is moving toward us very fast. And the order looks like this. A, the front end of the train enters, and then B, the front end leaves, and then C, the back end enters, and D, the back end leaves. Let's watch the exact same thing, but now from the tunnel's perspective. Remember, the tunnel is 1/3 of a mile long, and now to the tunnel, the train looks 1/5 of a mile long. Now the order is this. A, the front end enters, then C, the back end enters, then B, the front end leaves, and then D, the back end leaves. Notice that the order of the middle two has switched. On the train, it appears that the front end left the tunnel before the back end entered. In the tunnel, it appears that the back end enters before the front end leaves. Simultaneity is broken. The order of these events, they're not in the same place. The order of those events can change depending on your perspective. Time, length, order of events, relativity tells us that all of these are relative. So the big question, could you close the doors and contain the 1 mile train in the 1/3 of a mile tunnel? Einstein's strange answer is this. Yes, you can, but from the tunnel's perspective, the doors are closed at the same time. From the train's perspective, the doors are never closed at the same time. Is the train ever trapped in the closed tunnel? It just depends. Even that is relative. That takes us to our quick conundrum. Here's a plain board with 3 ropes attached. And you'll notice that the ropes are completely not tangled at all. Now, here's something I can do with this board. I can rotate it around 360 degrees. And if I do that, now you see that the ropes are tangled. I could try to untangle the ropes by moving them over here. Notice that I'm not spinning the board back. This one's untangled, but now the blue and the red one are not. And I could try to do something more. If you try this at home, what you'll find is it's always going to be tangled. Now the black and the blue are tangled up. No matter what you do, you'll always get tangled. Let me reset this. Now we're back to the beginning. If instead of rotating this once around, I rotate it twice around, something amazing happens. Here's once around, and now let me rotate it one more time around. If I do that, I can simply take these ropes, go up and over, without rotating the board again. I'm back to the beginning, and they're completely untwisted. You can do a demonstration of that with a mug, actually. So here the mug has the handle off to your left, and I can turn it around once. Now the mug has done a full 360, but my arm is twisted. But I can fix that by coming up and over my head and around. Once I turn 720 degrees, it's back to the original. The amazing thing is that this demonstrates something about subatomic particles. Some of those particles have what's called half-integer spin. And if you take something with half-integer spin and turn it around 360 degrees, it's different from what it started at. But if you turn it around again 720 degrees, now it's back to the original. For particles, these attachments, these are waveforms, and that's what's going on. The physics field of quantum mechanics developed over the early part of the 20th century, with figures like Einstein, Heisenberg, Born, Schrödinger, Pauli, Hilbert, von Neumann. The fundamental discovery about atomic and subatomic particles was this: small-scale objects and light have both wave-like and particle-like properties. On a human scale, particles, think of them as like billiard balls, they do one thing. And waves, think about water waves, they behave very differently. If a particle goes through a hole in a fence, it either makes it through or it doesn't. If a wave goes through a hole in a fence, it actually comes out the other side and it radiates out in a nice circular pattern. We think on our scale, two particles interact, they either hit or they don't, and two waves interact, they either interfere. Think about two boat wakes. Sometimes you get really large waves, and sometimes you get small ones. It's really important if you're water skiing. But atoms, electrons, these subatomic particles, they sometimes behave like particles and sometimes like waves. This is a highly mathematical, it's a very complicated theory. Today, we're just going to give a little bit of the intro to some of the most paradoxical aspects of these theories. We're going to talk just a little bit about the classic mind-bending physics experiment, the double slit experiment. If you shoot things, light, electrons, whatever it is, at a screen which has two slits, what comes through the other side onto some sort of target? The prediction from our common sense is that the particles will go through one of the slits, if they go through at all, and then they'll hit one spot somewhere on the target. But if it were waves, the waves would sort of go through both slits, and they would create circular waves around those slits on the backside, and those would interfere with each other. You do this experiment with hundreds of photons or hundreds of electrons at a screen, what do we see? Well, each one of those hits the target at some specific place. But on the target, it's not just two places that they end up. Instead, they form a pattern which matches exactly the interference pattern you would expect if they were two waves. So the best mathematical description of this is that each electron is best described by a probability distribution, where it's likely to be if you used a sensor to detect it. And that distribution is a wave that goes through both slits. It creates its own interference. Okay, so each electron is really a wave. That's strange. And remember, in order to see the interference pattern, we detect each electron as hitting in a particular place. But with thousands of trials, then we see the pattern emerging. It's like waves interacting, the high spots and the low spots, not just in the two places, one behind each slit. It gets more counterintuitive. You see, if you put detectors at the slits, then each particle goes through just one of the slits. The physicists talk about it this way. Each particle has its waveform, which tells you the probability of it being in any place, which is sort of a wave that goes through both slits. But when you detect the particle, the waveform collapses. It's like its wave-like properties sort of cease, and its particle-like properties dominate. But before you detect the particle, where is it? The mathematics says it's everywhere the waveform says it is. The particle isn't in a place, the wave is in many places. You shoot electrons or photons or neutrons at a double slit, without detection, each one goes through both slits. This is truly counterintuitive. The behavior of these things, are they particles? Are they waves? Are they both? It's just very different at their scale. These are things on the size of 10 to the minus 15th meters. Our intuition is based on objects at our scale. That intuition fails very badly at such a small scale. Before we go, one last modern physics mind-bender, and it's Heisenberg's uncertainty principle. New York Times contributor Jim Holt wrote this about Heisenberg's uncertainty principle. No scientific idea from the last century is more fetishized, abused, and misunderstood by the vulgar and the learned alike than Heisenberg's uncertainty principle. There are some really problematic descriptions of this principle. To measure something, you must change it. To measure a particle's position, you have to hit it and change its velocity. Maybe worse, Some things you just can't know. That's the way some people interpret uncertainty. Mathematicians and physicists, the uncertainty principle is just a set of mathematical equations. It's just a mathematical fact. If you get the mathematics, it's just straightforward. It's philosophically strange, but mathematically at least, it's very straightforward. Quantum theory says that a particle's position is a waveform, and its momentum is also a waveform. It's a different waveform. Momentum is mass times velocity. So a particle's momentum and position, these are two waveforms, and they're related. One is the Fourier transform of the other. The Fourier transform treats one function really, really nicely, and that's a Gaussian, a normal distribution. It's the same thing that comes up in statistics, a normal distribution. The Fourier transform of a Gaussian is another Gaussian, but here's the important point. The Fourier transform of a very narrow Gaussian is a widely spread out one. On the other hand, the Fourier transform of a widely spread Gaussian is a very narrow one. And here's how that ties into Heisenberg's uncertainty principle. Remember, a particle doesn't have a position. It's a waveform that tells you where you're likely to find it if you detect it. Now, a narrow Gaussian for position, that means you know very well where the particle is. But that means there's a wide Gaussian for momentum. The velocity is not very well pegged down. It goes the other way too. If you have a very narrow Gaussian for momentum, that means you know the velocity very accurately. Well, its Fourier transform will be a wide Gaussian for position, so the location is not very well known. There's an extreme case you could think about. If you know the position exactly, what happens? The mathematics says the velocity might be anything. We know nothing about it. On the other hand, if you know the velocity exactly, the location might be anywhere. We know nothing about its location. This is a simple mathematical relationship with a real profound implication, Heisenberg's uncertainty principle. Like relativity, these quantum mechanics paradoxes are incredibly counterintuitive. Only incredibly careful experiments have gotten us to reject the common sense that our everyday interactions at our scale, at normal speeds, have given us. We have to fight past the common sense. We have to unravel these paradoxes, and that helps progress physics into the modern era. Next time, we're going to turn to some geometrical puzzles and paradoxes.